Hey everyone, welcome back, and today let's solve Leetcode problem 11 titled Container with Most Water. So we're given an integer array height of length n, and there are n vertical lines drawn such that the two endpoints of the ith line are I, 0 and I at height at I. We have to find two lines that together with the x-axis form a container such that the container contains the most water. And we have to return the maximum amount of water a container can store. And notice that you may not slant the container. So honestly, a pretty complex problem when you just look at it from the problem statement, but it gets a lot simpler and a lot more clearer if you just dive straight into the examples. So they actually give an image for the first example to help visualize how this would actually be structured. But as you can see, we just get inputted a height array of the different heights of each line. And we'd have put 49 in this case, right? Because the above vertical lines are represented by the array 186254837. And in this case, the max area of water, the blue section highlighted, is going to have a area of 49, right? Basically 7 times a width of 7, and 7 squared is going to be equal to 49. You just have to maximize the amount of water that can be contained, right? And in example 2, we have heights to be just 1, 1, and so of course we can only have a area of 1, and so the max amount of water that we can contain is obviously just going to be 1. Okay? So with that problem statement out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem. Alright, so the main idea behind this solution is quite simple. It's not as complex as it seems. Basically, we're going to be using two pointers to represent the left and right edges of a container, or endpoints if you will, and the height of the container is going to be determined by the shorter of those two lines at each pointers, and the width is going to be the distance between them. And we're basically going to move the pointers toward each other, always trying to maximize the area as much as possible to optimize our solution. So again, we'll initialize those two pointers, one at the beginning and one at the end of the array, similar to binary search. And we'll basically have a variable most, or whatever we'd like to name it, to keep track of the maximum area found so far. And we'll just have a while loop that runs as long as the left pointer is less than or basically within bounds of the right pointer. And inside that loop, we have to calculate the area between those two pointers, compare it with the current maximum area as updated in the most variable if needed, and move the pointer that points to the smallest height inward, since moving the larger height would not increase the area, it would only decrease it. So let's just break down the code line by line and better explain what this actually does. So again, similar to binary search, we're going to have L and R, since our input is an array of heights, to be equal to 0, and the length of the heights minus 1. Actually, I think it's just height, right? Yeah, it's just height. Okay, length of height minus 1. Okay, and L is going to basically point to the first element in the list, or the 0th index, and R is going to point to that last element, or the length of the height minus 1 index. And we're setting these pointers to start from opposite ends, and we're going to gradually move them inward or towards the center, where the setup is key to our two-pointer strategy, because that's going to reduce the time complexity from big O of n squared, or brute force, to big O of n, because of this two-pointer technique, right? That's why the two-pointer algorithm is so key, okay? And we're going to have a most water to be equal to basically 0, right? Because we haven't actually traversed through the array yet to find any possible combinations of our lines, okay? And again, this variable is going to keep track of the maximum area found between different lines during the traversal. And initially, again, we're going to assume that the largest possible area is 0. And as we explore different container shapes, we'll update this value if we find a larger area. Okay? Now we'll have our while loop to check while the pointers are in bounds of each other. So while L is strictly less than R, it can't be equal to R, because then we don't have a width and height. We just have a width, or we just have a height. We wouldn't have both. We need to have at least two different dimensions. Okay, so while L is less than R, again, this while loop basically runs as long as the left pointer is strictly less than the right pointer. So we have a valid window, or a valid area. And this ensures that we keep checking different container sizes by moving the pointers inward. And once the two pointers meet, we know we've checked all possible areas optimized between the lines. Okay? So once we do that, while L is actually less than R, we'll set the most water to be equal to the maximum value of course, most water, because we don't want to make it smaller for any iteration. And then finally, the r minus L, actually I'll put this in parentheses, r minus L, right, basically the width of this current window, or the two lines, multiplied to get the area of the minimum of height at L and height at R. Okay, and this is basically telling us the area of this current window in this iteration to check if it's greater than the most or highest area we've seen in previous iterations so far. Okay, so minus height at L and height at R. Okay, and the reason why we do the maximum of R minus L times this is because R minus L is going to be signifying the width of the current window between the two lines L and R in this iteration, right? Because if we had L to be here and R to be here, the width is simply R minus L. And we do R minus L, or the width, times the height. And the reason why the height is signified as the minimum of height at L and height at R is because, let's just say that our L and R are here again, using the same example. R is going to have a height of 7, and, height of 7, and L is going to have a height of 8. Obviously, our height is not going to be 8 because we can't contain more water than a height of 7. This could contain 8. Our left pointer could contain 8 water, but our right pointer has a maximum of 7. We can't exceed 7, and so we'd actually have to take the minimum of those two heights at those two pointers of that window just to ensure that both of our pointers or endpoints can actually contain that water without overflowing, right? In this case, if we had the maximum, then this would overflow, right? Because 7 is less than 8, and we can't contain water 8 in a height of 7. That wouldn't be allowed, okay? That's why we'd have to do the minimum of those two heights of the two pointers or endpoints to actually get the accurate area without overflowing our two pointers, right? This basically stores the accurate height for these two pointers, okay? So once I actually initialize that most water area, now I actually have to increment or go inward in my two pointers. So if height at L is actually less than height at R, then I know that I can actually shift inward with my left pointer because my left pointer is right now less than my right pointer. So I'd have to do L plus equals 1. Basically go rightward or inward in my array, okay? And basically if our left pointer is actually smaller than the height at the right pointer, then we can move the left pointer one step to the right by increasing L by 1. And the reason why is because we have to move the smaller height that is moving the larger, because moving the larger height wouldn't actually help us find a larger area. It's the smaller height that's actually the bottleneck, right? We have to actually change that smaller height and move rightward to actually get a larger area than we've found so far, okay? And basically, if that's not the case, so we'll have an else statement here. If that's not the case, then we can simply decrement our R by 1 to explore larger areas in the left portion of the array. And ultimately, outside of this while loop, once we've explored all different possible areas for all different optimized windows in this input array height, we can return the most water found. So as you can see, if I were to submit this, unless I made any syntax errors here, this should be accepted. And as you can see, this is just about as efficient as you can get. I feel like I haven't explained line 6 as good as I could get it to be, so I'll just kind of reiterate what I was talking about before. Again, this is where we're calculating the area of the container formed by the two lines or pointers or endpoints, if you will, of the current window, L and R. And R minus L is going to give us the width of the container. And the minimum of height at L and height at R, the two heights of our endpoints of our window, is going to give us the height of the container, since the shorter line determines the water level, so we don't overflow. And when we compare this current area with the value in the most water using that max function or method in Python, we have to update the most if this area is larger than we've seen before in previous iterations to actually accurately maximize the total area found of every single optimized window. Okay? So to better overall explain what this code does, we basically start with two pointers at the beginning and the end of the array and gradually move them towards each other, where at every step we'll calculate the area of the container formed by the lines at these two pointers, right? And the pointer with the smaller height is moved inward because moving the larger height will never help us get a larger area. It's limited by the smaller height. And so the process continues until the two pointers meet, and the largest area found during this process is ultimately returned, that's stored in the most water variable. So for the time complexity of this code, this is going to have a big O of n, or linear time solution, for a runtime complexity, because N is going to be the length of the input array height, because this is only a one-pass solution where we traverse through the array once, with each pointer moving inward exactly once, right? And for the space complexity, this is going to have a big O of 1, or constant time space complexity, since of course we're only using a constant amount of extra space, just a few variables for pointers and the maximum area. We're not actually using any extra data structures to store any elements as we parse through or process the input. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I'll see you guys in the next one. Bye-bye.